Our next speaker, Anne Almgren, she was at Livermore and moved to Berkeley when NERSC moved to Berkeley in 1996. So she was at Livermore in the Applied Math group, and she's currently a member of the Center for Computational Sciences and Engineering in the Computational Research Division here at the lab. Anne works on development and implementation of algorithms for solving numerical PDEs for fluid dynamics with applications to astrophysics, cosmology, and low Mach number flows. She's a primary developer of Castro, Maestro, and the NYX codes, who all of us who work at NERSC know very well. Did you pronounce it?
Nix.
Nix. And all of which have used many hours on the NERSC machine. So welcome, Anne.
So I started at Livermore in 1992. I was a graduate student at Berkeley, and then I went to Livermore as a postdoc, and Mike Welcome was a member of the Applied Math group that I joined in. And this is a picture apparently from 1998, so this is the way that I remember Mike. And we had a lot of fun. Actually, I was thinking about it. I was remembering the way we worked at Livermore. We had these offices across the hall from each other, and of course nobody had two screens at that point, which I think many of us do now. And the debugger would take up pretty much one screen, and so we had debuggers, then it wasn't that ancient history. And Mike and I would each bring up a run on our screens, and we'd yell across the hall. Okay, Mike, you read the left column. And he'd read his numbers, and then I'd say, stop, okay, that one's different. The thing I was trying to remember, and I want to poll the audience here, the debugger we were using, the only thing I remember about it was that you could set the palette, and you had options like Monet and Cézanne. Does anybody remember this one? Okay, if you think of it, let me know, because it's driving me nuts. Because I just remember you could get these nice pastel colors in your debugger, and they had such a selection. It just, anyway. So we will all miss Mike. Okay, this is something completely different from what David talked about. This is one of the application areas that I work in. I apologize, it's a little bit of a revisit of a talk I gave at Supercomputing in 2012. And it's an example of one of the types of things we do. It's low Mach number models in computational astrophysics. I am not an astrophysicist, so a number of things I say are things that my colleagues have taught me. When we get into the algorithms, that's where I really know what I'm talking about. So the question is, so what do? We want to study astrophysics. We want to study certain types of phenomena. And when you think about astrophysics, you tend to think of things that blow up. And so the first thing you say is, if it's blowing up, it's sure as heck not low Mach number, because the Mach number is the fluid speed over the sound speed, and when things blow up, they're going really fast. So why would you ever use a low Mach number model for astrophysics? And the answer is, for a lot of simulations, you wouldn't. And the type of things that we think about with astrophysics, we think about novae, we think about supernovae, we think about gamma ray bursts, or maybe we don't think about those, but those are things that blow up. X-ray bursts, those are all very compressible, very explosive phenomena, and they're the ones that make astrophysics really interesting. The one I want to focus on, we actually have modeled several of those. The one I want to focus on is type 1a supernovae. And there's a whole hallway of people, actually this floor even, who know a whole lot about these. So I'm going to give sort of the cartoon version of the science and why you would care. So what are they? They are the largest thermonuclear explosion in the universe. So that's kind of neat. The brightness of a single star. So a supernova is a single star blowing up. At its peak, it rivals the brightness of the galaxy, which is many, many stars. So it gives you an idea of the amount of energy involved. And the first question I asked, of course, when someone said type 1a, well, why is it a type 1? Why is it a type A? So being a type 1 says there's no hydrogen line in the spectrum. 1a has to do with the silicon 2 line. Okay. So that is the thing that we want to model. So why would I use a low Mach number code, a code that is designed to model things that move slowly? Okay, the answer is that explosions don't come out of nowhere. There's this build-up period. There's something that gets the star to the point of exploding, and so there are these long periods of very non-explosive fluid dynamics. And those are characterized by low Mach number flows. They're convective flows, which means what you care about is the fluid motion, as opposed to the acoustics, the sound waves rattling around. And it turns out that we actually care about what happens before the explosions. It sets the initial conditions, and so we need to be able to understand and simulate both types. So the rest of this talk is going to be talking about the type 1a supernovae, but a lot of this applies to other things that we do. Okay, here is the cartoon version of the physics. Why do you care about type 1s? Okay, so you have several choices for the universe. It's expanding, it's not expanding, it's static. And in any one of those cases, you can ask, if it's expanding, is it getting faster or slower? If it's compressing? Is it going to turn around? So we want to know what's going on. So originally, back about 100 years ago, Einstein said, no, it's static. Okay, that kind of makes sense. That's what everyone will go to first. 1929, you have Hubble observing that galaxies are in fact moving away from us. Okay, so that says the universe is expanding. So that's the first of three choices. Now we want to know, is it expanding at a constant rate? Is it going to get faster? Is it going to get slower? So now you've got a bunch of observations. You look at the rotational speed of galaxies, orbital velocity of galaxies in clusters, gravitational lensing. All of these things point to the fact that there's something else out there besides what we see. There's mass there that we haven't accounted for. This is the old, I was a physics major as an undergrad, and I still remember, if you want to know the stone spinning around in the string, you've got this mv squared over r. Well, so m's got to be bigger than what we can see. So now we have dark matter. Matter that we don't know what it is, but it's got to be there. So now that says, well, there's all this mass there, we're expanding now, but maybe we are headed for the big crunch. Okay, and so 1998 Science Breakthrough of the Year, 2011 Nobel Prize. This is the whole supernova project, the supernova cosmology project, the HISE supernova search team. I'm trying to give the credit where credit's due. This is the very short cartoon version. If you say that all supernovae are the same, if you believe they're the same, there's a way of mapping the duration to the absolute magnitude. If you know the absolute magnitude and you know the observed magnitude, the apparent brightness, then you know the distance. You know how far away it is. And if you know the distance and you know the redshift, you put those on a plot, you get a Hubble diagram. And what that tells you is that, make sure I can say this right, the older objects are not moving away from you as fast. Therefore, the rate at which the universe is expanding is increasing. So this is huge, because now there has to be something to balance all the dark matter. And so because we don't know what that is, we'll call it dark energy. So there's all these fundamental questions of the universe, and if you sort of look back, there's this thing in red, there's standard candles, where we said, so supernovae behave now the way they've always behaved and they always will behave. It would be really nice if we understood how they blow up, because we're putting a whole lot of faith in them, concluding that there's dark energy, but we really don't know how they start or how they blow up. And is there any reason to assume that the stars many, many years ago blew up the same way they do now? So if we understood that, we might have some more confidence. For a while, there was this was sort of the dominant progenitor theory. I would say in the last couple of years, a number of other progenitors have been explored. This is the one that we have looked at. We are actually in the process of looking at several others. So a popular but not the only model for where an type 1a comes from is the thermonuclear explosion of a carbon-oxygen white dwarf. And the picture of this is that the carbon-oxygen white dwarf is accreting mass from a binary companion. And so you have this binary system. This white dwarf, it's under the Chandrasekhar mass, which is the critical limit. It very, very slowly accretes mass from the red giant companion. That's on the order of 10 million years. So one of the things, if you want to do a simulation, you got to know what your time scales are. We're not going to simulate 10 million years. So as it gets bigger and heavier and the pressure in the center of the star increases, over a period of centuries, the carbon burning near the core drives convection. So slowly this thing starts to, see, it's not simmering yet, I'm not sure what the appropriate word, but slowly things are starting to move. You've got heating at the center, you're starting to circulate. Over the last few hours, the convection becomes more vigorous. You have the heat release, the heat generation at the center is intensifying. The convection can carry the way the heat so fast, and initially that's enough that it keeps it just very, very slowly heating up. Heat release becomes more intense, convection becomes more vigorous. Eventually, the convection can't take away the heat fast enough. And that's what we call ignition. So ignition is where you hit this critical temperature, and then within seconds, it blows. So you've got really disparate time scales here. You've got this century, or you've got this millions of years, centuries, hours, and ignition. So we are not so ambitious that we're going back to centuries, but we would like to go back a few hours. Okay, so if you follow these things, you know that people have announced, we've solved supernovae. We've simulated these, done. We know how they blow up. And if you look more closely, what they have simulated is those last 2 to 3 seconds. And so how do you do that? So this is a time slice. This is not our work. This was at the University of Chicago. And the red here is it's probably a temperature contour. And so what it shows is you have an initial condition of some sort. You let it evolve. This red, this bubble will push out, break out, the whole thing will explode. Okay? So this is great. This is an exploding star. And how do you start this? Well, you have to know what a star looks like. And so you take a 1D profile you have a 1D stellar evolution code. You map that into a 3D star. That gives you the radial profile of the star. That's probably pretty good. Well, then you have to ignite it somewhere. And the thing that turns out, you have to make some assumptions here because you don't know where it ignites. And the problem that we have is that the answer depends on the initial conditions, which if you've ever run simulations, you find sometimes happens. And so here, this is an example of central ignition. You say, stars are hottest in the middle because that's where the pressure is hottest, and that's where you typically think of the things being hot. So we will ignite it in the center. And if you ignite it in the center, you get a very specific kind of explosion. And it turns out if you ignite it off-center, you get a different kind of explosion. And so nobody had really addressed the question of, well, how do we know where it ignites? And does it ignite 10 kilometers off the center, 100 kilometers off the center? That matters, it turns out, in terms of whether you can even get a realistic supernova out of this type of progenitor. So we really need to know, because what we know from all these compressible simulations is that it does matter how you start it. So that's why we care. So what do? You go back to the drawing board and say, okay, so we know how people model supernovae. And basically, this is the compressible Navier-Stokes equations. We can write them down very easily. We've got density, velocity, pressure, energy. The only thing that's actually really complicated about this is the equation of state. It's not a regular gamma log gas. It has certain degeneracies. But people kind of know what that is. So you write that in, you put it into your code. And it's a really nice thing to program and run. And so in fact, the Castro code solves these equations, and it's used for, you can use it for type 1a explosions, so that's been done. We have a lot of collaborators who are actually using it for type 2, which are the core collapse supernovae. And I think it wasn't you. Somebody called me up once and said, so Castro's running on NERSC and it's taking 10% of the machine. What are you doing? I have no clue. Something to do with type 2s. We've got collaborators running these things pretty often. But anyway, this is a great thing to program and run because you write it down as a conservation law. U is your state variable. You update it with fluxes. You can use a time explicit method to solve this. It's easy to program. It's easy to parallelize. We've done this. We got up to 200,000 cores. I should have made that not on NERSC. And it's straightforward. So we do a lot of things with AMR because stars, it turns out, are not uniform, and you really want to zoom in on the center of the star or the region of interest and not all of space. So we use adaptive mesh refinement for these. And this is great. So we know how to do this, and it works great for modeling those first 2 seconds. The problem is those 2-second calculations, when I showed you the cartoon of, those were hero calculations. Now, granted, they're 10 or more years back now, so they're not necessarily hero calculations today, but 2 seconds was the limit. So now we say, well, we really need to go back 2 hours. Nobody has the patience for that. So that's where, for me, the fun begins. Oh, one more slide. So this is just a statement that, well, of course, we have supercomputers. This is a supercomputing conference, so I had to say the word supercomputers. So we have AMR. Isn't that the answer to everything? You just zoom in, and you don't need to resolve the whole thing. Isn't that wonderful? So the problem is, of course, that when you run an explicit code, you have a time step constraint that is limited by, so delta x is the mesh spacing, u, fluid velocity, c, sound speed. As the mesh spacing gets smaller, the time step gets smaller, and that 2 hours takes a really long time. And so with a method like this, you can't beat the fact that you're not parallel in time. And yes, there are parallel in time methods, and that's a whole separate thing. But this will just take too long, even with lots and lots of processors, even with perfect scaling. So I'm not that patient a person. So we say, okay, let's go back to the drawing board. I showed you the compressible equations. Those aren't going to work. So now we want a new model. And this, to me, is where it gets really fun, because we say, okay, what do we care about? Well, we don't care about the acoustic waves, because when this thing is churning, the acoustic waves are bouncing back and forth across the star. They serve to equilibrate pressure in a specific way. But we don't need to resolve them. We don't need to resolve them the same way that if you want to do a model of the heat flow in this room, and you care about, well, maybe you as individual people are generating a little bit of heat, and that's driving convection in the room. You might want to have a great model of this room. You don't care about the fact that I'm talking. Right? There's acoustic waves bouncing around. They're irrelevant to the solution, and if you track those, you would never find out whether you need to turn on the air conditioning. Okay, so it's the same thing with the star. We just don't care about those, but they kill the time step in a compressible code. So what we want to do is analytically get rid of those. Okay? We want to get rid of the sound waves, but we don't want to get rid of, analogously, we don't want to get rid of the fact that the individuals in the room are generating body heat that is making the air rise. So the same thing here, we say, okay, what's our wish list? Well, obviously you have to have buoyancy, you have to have hot things rise. You have to allow for the fact that the star is radially stratified. It's much denser at the center of the star than it is at the outside. You have an equation of state that's kind of funky, so you can't make any gamma law assumptions. You've got heat release, you've got reactions, you've got a lot of heat release, you've got to have that make the fluid less compressible and therefore buoyant. And you've got to let the star puff, because these things do actually puff out before they explode. There's just an overall expansion of the star. And so you want a model that does this, and the whole point, of course, is that you can run it with a bigger DT, and therefore you can solve it in your lifetime. So lower time, it's all about time to solution. I want to get the answer so that I can use all those neat techniques to understand what the science is telling me. Okay, and the question is, gosh, I've heard about these things, and don't these models exist? This is just a quick chart to say, yes, there are a whole lot of models along this spectrum. If you look, so the general category is low Mach number models. Incompressible is one limit of that, and then anelastic is used a lot in atmospheric modeling. You might hear that one. A Boussinesque is a simpler version of anelastic. Pseudo-incompressible is another, something that's very common in atmospheric modeling. And each of those fails to allow for one of the features that we need. And in fact, in atmospheric modeling, it turns out that the temperature differences are not that high. So, in modeling climate flow or just weather prediction, you don't have the kinds of extremes in temperature that you do when a supernova is about to ignite. Okay, so that works great for the atmosphere. It doesn't work when you're trying to explode something. And again, the background state is something that was new. Okay, this example is just to show that if you aren't careful, you can be really wrong. Okay, so this is just people pointed out to me more than once, it's a bubble rising. The pictures at the top should be at the bottom so you get the sense of rising. So this is a time series where time goes down, and there are 4 different models here. On the left is what a compressible code would give you. So that is just a classic bubble. If you go from the upper left to middle left to bottom left, that's a classic bubble rising in a kind of mushrooms like that. This one's just a 2D. In the second column, you see the picture of the low Mach number method. And what you'll notice is that the shape is roughly the same, the height of the bubble is roughly the same. And in fact, if you look carefully, it's actually interesting. You can see that the compressible bubble is wider. This drove us nuts for years. And in fact, this year, we finally figured out why. Actually, somebody else figured out why. But if you say, well, those other models, weren't they good enough? They were already out there. So yeah, anelastic model. Anelastic model puts in a linearization of the effective temperature on density. It turns out the bubble just doesn't rise enough. So you put in that model, you'll get the answer wrong. Incompressible gets the buoyancy right, but doesn't let the expansion happen correctly. And it basically, it does something completely unphysical. So the point of this is that simple models weren't enough. We needed to come up with a new one. And what happens, the way all low Mach number models are derived basically, is the observation that if the flow is slow, if the Mach number is small, then we know by asymptotics that the pressure has to be relatively uniform. And I say relatively uniform because if you're doing a combustion calculation, the pressure is a constant in space. You don't have large gravitational effects. So there's a pressure that may grow in time if you're in a closed chamber, but it has no spatial variation. If you're doing a star, the pressure is very stratified. It has a dependence on the radius or the elevation in the atmosphere and time. And then you have a pressure perturbation. So this is true for all low Mach number flows. If it wasn't true, then that pressure perturbation would accelerate the flow. It wouldn't be low Mach number, so you're safe. And the assumption you make is that background pressure is what enters the thermodynamic relationships, and the the perturbational pressure pi is what affects the dynamics. Physically, what happens is the sound waves, instead of tracking them as they move across the room or across the star, you just say they equilibrate instantly. So every time step, you equilibrate the sound waves. They still affect the solution, but they affect them instantaneously. You're not tracking them as they march across. And so we say they're filtered out because sound waves are no longer a solution to the equations. Okay, mathematically, what's happened is you've changed your equation set. You've introduced a constraint, and that changes the character of that, and that's going to require some additional solution techniques. But computationally, you've got what you want. If you advance the method designed on these equations, you march it at the fluid velocity, not the acoustic velocity. And that's what we wanted. Okay, what does it look like? It looks very similar. In fact, the first three equations are pretty much identical, pretty much. The fourth one is a constraint on the velocity. And that says the velocity can expand due to a bubble rising. It can expand due to heat release. It cannot expand because an acoustic wave came through and tried to push on it. And these other variables just have to do with the heat release and the compositional change and everything. And then at the bottom, we want to expand the star as well. Okay, whoops, that would be the wrong way. Okay, so there were three codes mentioned in the introduction. Castro is a compressible code that we wrote that people are using for supernova mostly. Maestro is the code that we wrote for this. And then Nix is a code that's now, I think, burning the most hours on Edison. Look at Dave, he's not looking. I think it was, Nix was a code that was just featured in the Edison early science results. And it turns out that, that they share a lot of infrastructure, which is a convenient thing for us. Anyway, so the numerical approach is based on generalized projection method, which may or may not mean anything to you. It's second order accurate, which is what you need. It has the same way of handling the reactions as the other codes, so we kind of know that that works. And then this last part is just a plug that in CCSE, we have a software framework called Boxlib. And again, going back to Mike Welcome, Boxlib was something that we developed back at Livermore. And the funny thing is I remember the discussion of saying, well, we really need to make Boxlib parallel. I remember thinking, parallel, I don't know, we can put that off for a while. But so for a while we had P-Boxlib, the parallel version of that. And it's kind of hard to imagine now that we ever had a non-parallel version. I don't remember that actually. But it's a code that supports block structured AMR. So it has the structure to, you can do anything with unions of grids. You can do anything with unions of grids across multiple levels. It means you don't have to rewrite all those parts of the code every time you write a new one. This is the Castro code scaled over 200,000 processors. It has these linear solvers for solving elliptic and parabolic equations. It turns out those don't scale as well. So that's the price you pay. I mean, there's always a price. We march at a much higher time step, but now we have to do linear solvers. And anybody who does this knows that conservation laws work really well. Linear solvers have issues. But I'd say we scale up to maybe, let's say, 50,000. So we do a pretty good job. It's hybrid MPI, OpenMP, and then because basically we have plug and play equation of state reaction networks. Because you're never quite sure, well, this was a carbon oxygen white dwarf. What happens if we put in a little bit of this? What's the magnesium reaction? You want to be able to play with that. Okay, so physically, again, we said acoustic waves are no longer there. You've got the other physics that you want. Mathematically, you've changed the character. Computationally, you've got the DT you want. But you now have this linear, the elliptic equation you need to solve. And so we do use multigrid. Multigrid plays very well with AMR because AMR levels can look a lot like multigrid levels. So it's a very nice iterative technique. And it turns out that is the linear solver is what takes most of the time, not surprisingly. But I made the statement that in the end, we care about time to solution. And I will tell you that we can do a calculation with Maestro that we cannot do with Castro. So that answers the question, is it worth it? Okay, so now for the fun part. How am I doing on time? Oh, we're good. So there's a question that we want to answer, which is, what are the initial conditions for these explosions? So we go out, we say, okay, we're going to make a new method and build a new code to do this. We do that, we verify and validate and verify along the way, and then we run a simulation. And some of the things that Data was talking about, that David was talking about with data, there's always this trade-off of you really want to be able to just look at the data. I love looking at the data and saying, speak to me, what do I see? Well, okay, so now I've got too many numbers to do that. I know I care about the velocity field, and I know I care about where it ignites. And it turns out that one of the hardest things to do with this one was to look at the velocity field. Because it's not a nice, simple flow, and if you set the thresholds too high or too low, you miss features. You don't want to set the threshold, say, ignore all velocities under some amount because you might miss little eddies that are very important. But you want to get a big picture, and it's 3D, so you don't want to block out something that's happening behind. And this was actually, I'd say, in some sense, we hand did it. So we played with Visit, and we just kept doing it over and over until we made movie after movie to say, can you tell what's happening? And if you can come up with a service that will just do that, that would be awesome. Unfortunately, I would say we didn't know what we sort of knew what we were looking for. We posed some hypotheses and then said, okay, does this look like it? No, it doesn't look like it. So anyway, these are both from one simulation. We wanted to know in the inner 1,000 kilometers of the star, what does the flow look like? So it turns out that people had done some very modified, some small-scale approximations to this. They'd cut out the center of the star and then had flows that went through the center of the star, which I never quite understood. So there's a question is, does ignition happen right at the center because that's where it's hottest? And then everything just kind of goes radially outward. That's one picture of it. And the answer, let's see if I can make this go. There we go. So believe it or not, this is the best movie that we came up with. Red is outward flowing, blue is inward flowing. So you can get a general idea. There is a sense of a dipole. Okay, and that's something that had been predicted from some earlier simulations, not by us. They said, we think we see this dipole flow. And in fact, if you look, there is a coherent red structure coming out. There is not a coherent blue structure going in. So what you can imagine is the fluid just sort of gets sucked in from everywhere else. It gets pulled in, it jets out through the center. So now if you say, okay, so we believe there's a dipole, and in fact, if you do a bunch of diagnostics on this, you find that it's not a consistent dipole. It doesn't just sit there in one direction. It sort of, it's precesses, not really. It sort of moves around. And so then there's a question of, well, how does the location of the dipole affect where you ignite? Because you might imagine that it's carrying the fluid that's just been heated up, and so it's going to push it out, and then it's going to go boom. You might imagine that. Again, we just play that one more time. That one doesn't tell you a whole lot except that things are moving out from the center. So anyway, what we finally ended up doing. So then how do you define ignition? Because you can't let the Maestro code ignite because it doesn't solve the equations once it's ignited. So we had to define ignition. So we said, okay, ignition is where it gets above 6 times 10 to the 9 degrees Kelvin. And we want to know, we say, okay, so the minute that happens, we have to stop the simulation because then we're outside our range of validity. We say, well, gosh, if you get pretty close, then maybe you're a potential ignition site. And so what we did is, through the simulation, we monitored the peak temperature and where it was. And we made this histogram. So we filtered this, we binned the data, and what you're seeing here is the color coding is by the temperature. What this shows you, if you look at this, is that the hot spots occur in a relatively narrow band of radii. And so you can say with some confidence that the supernova is most likely to ignite somewhere around 0.5, that's 0.5 times 10 to the 7 centimeters, from the center of the star. This is something that had not been known at all. And again, the thing I showed you before was a centrally ignited ignition, where you say it's going to ignite right at the center, we'll watch it move out. It turns out it doesn't. Okay? The other thing that you want to know is, at these locations where it's igniting, what's the flow like? Is it, in fact, caught up in the middle of the dipole? Is it off to the side? Is it dropping inwards? And just because this was not actually an astrophysics talk, we again tried to get a feel for what the velocity field looks like. And what you can see here is this is a cartoon that we made. There is this dipole coming out, and it turns out that, yes, the ignition does happen in that range. And there's a bunch of circumferential flow at the outside. You've got some buoyancy. You've got a little bit of turbulence. It turns out through some other studies that the turbulence is not as big of a factor as that we thought it might be. But the point is, we got a cartoon of how this works. And I hesitate to show this because it was not a NERSC simulation. But what we were then able to do was to say, okay, let's take that information, the ignition radius and the velocity field, let's use that to initialize the Castro simulation, which is the compressible code. And so we take it from convection to breakout. This is something that was done under a Blue Waters grant and actually initialized it, quote, correctly to say, how do these things blow up? And that's something that was done by Chris Malone, who is starting at Los Alamos, I think, as we speak. And then, just as a summary, so again, we had the science problem, said, okay, can't do it with the existing codes, new model, new code, and all the bells and whistles, AMR, hybrid parallel. And then, of course, once you've built this code, you say, what else can we do? And so that's one of the things Maestro is still running. We've put the particular type 1 to rest, I think, and we're looking now at some of the other progenitor simulations, progenitor candidates to say, can those create the type 1s that we see? Chris Malone, again, has done a bunch of type 1 X-ray bursts. We had a graduate student working with us that did convection in main sequence stars, because stars are always convecting, even if they don't blow up, and you would like to understand what that convection looks like so you can understand, understand the stars, basically. And then there's a lot of things about understanding the nuclear burning as well. And that is the end. Thank you. I think we got the break early.
Yeah, so we have some time for some questions, if there are any.
Yeah.
So, were you able to correlate anything between your simulation results and observations of a supernova?
So it is a process, right? So we generate the initial results for the compressible simulation. The compressible simulation generates an explosion. The thing that we observe are the light curves. And so there's another step, which is to say, take the simulation results, generate the light curves, compare those to specific observations. That part of the puzzle we have not been involved in. The light curves, like Dan Kaysen does a lot of that. So we have not followed it through to say, wow, this simulation matches this supernova observation. We have not personally done that. That's where you want to go end to end, though.
I mean, or even just, you were talking about the explosion sort of happening on one side of the star. I mean, if it happens toward you, do you get one thing? And if it happens away or at an angle, do you see something else?
So with these, I think, one scenario is, this is what the University of Chicago people had, it comes out very much one-sided. It wraps around the star, and there's one version where when it meets on the other side, that's what actually trips the explosion. I think that the explosion itself probably masks any of those directional effects. A lot of things that they observe are it's how much was burned versus, how much of different elements were burned versus unburned in what we see. And unfortunately, we've probably pushed up to the limit of what I should try and say about that, because that part's kind of beyond me. So we have not, what we would ideally do if they kept funding us to do astrophysics is to create that end-to-end, where we could do a simulation, we could say, does it match any of these actual observations? Because that's the whole point. That's what we're doing, is you get these observations and you want to use those to tell you how the supernova exploded. And what you have to do is you have to run simulations and say, okay, here's one version, does it match? Okay, we'll tweak it, here's a different version, does it match? And then now it turns out that there's more variety in type 1As than people thought. So it becomes a much more interesting question, and they stopped funding us for astrophysics. So.
Thanks, Jed. I know that Peter Nugent and some of the people have looked at asymmetric explosions and tried to figure out what the observational signatures of those would be. Right.
And again, I've presented a very simple version of a cartoon of what's going on in supernova research. So,
my question was pretty much the same as Jed's, about whether type 1A that are dipoles, will they give us more information about the universe or less than ones that are flash bulbs? Or maybe what you just said is...
The dipole flow, I was just talking about the flow, that early flow of how it ignites.
So the light is actually still like a flash bulb? Non-directional.
Right, so the thing that you really, so what you see in the light curves is how much of the star has burned before it exploded. So you can imagine if you had a flame propagate out from the center, a flame that went out like this, burned through the star, and then the star exploded, then the star at the state of explosion is actually very different than if you maybe shoot a burning bubble out this way, it wraps around the outside, and most of the star is unburned. And so I know with the light curves, that's what they can really tell is what relative fraction of elements do they see. So one of the things we know, for example, is that you cannot, there's something called deflagration to detonation transition, that has to do with how much of the star burns before it detonates. And that's really, I think, what they can tell you is if you get those fractions wrong, then you have an unrealistic scenario. But again,
Any other questions? If not, let's thank Ann again.
Thank you.